Your roof is lying to you every single night. Not the shingles, not the joists. The layer you were told would protect you, the pink stuff, the spray foam, the product a contractor pointed at with confidence and said, "That's your thermal barrier." Right now, while you sleep, heat is flooding in through the ceiling in summer and bleeding out through it in winter, and the material sitting up there is doing far less than its packaging claims. There's a particular kind of heat that settles into a poorly insulated attic. Thick, pressing, the kind you notice the moment you open the hatch. It smells like baked dust. It sits on your skin before you're even all the way up the ladder. It tells you something is wrong. Attic temperatures in poorly managed roof lines can exceed outdoor ambient temperatures by 40 degrees Fahrenheit or more on a clear afternoon. That differential doesn't stay in the attic. It migrates. Slowly. Relentlessly. And it works its way through your ceiling into the rooms where your family lives. The Anasazi, the ancient cliff-dwelling builders of the American Southwest, knew exactly how to stop it, without a single roll of fiberglass, without a single spray can, without a single product manufactured in a facility that needed electricity to run. What they built still stands. What you bought degrades every year. The insulation industry's argument is built on a single metric, R value. R value measures thermal resistance, how well a material slows the movement of heat through itself. The higher the R value, the more it resists. The industry will tell you that a well-insulated attic needs R38 to R60 depending on your climate zone, and that fiberglass bats or blown-in cellulose are the clean, code-compliant way to get there. What they don't tell you is that R value is a laboratory figure. It is measured under controlled, static conditions, constant temperature on both sides of the material, no air movement, no moisture, no compression. The moment fiberglass is compressed even 10%, its effective R value drops proportionally. The moment it absorbs moisture, and it does because it is hygroscopic, meaning it actively pulls water vapor from the air, its performance degrades further. A 2019 review by Oak Ridge National Laboratory found real-world fiberglass bat performance routinely running 20 to 40% below stated R value in standard residential installations. That is not an edge case. That is the norm. Your insulation was never performing the way the label said. The Anasazi built their great houses into the faces of south-facing sandstone cliffs in what is now the Four Corners region of the American Southwest, between roughly 900 and 1300 CE. For 4 centuries, they engineered shelter that stayed cool during summer days that exceeded 100 degrees Fahrenheit and retained heat through desert nights that dropped near freezing. They did not use resistance. They used mass, specifically, the thermal storage capacity of dense earthen material placed in deliberate relationship with the sun's angle and the rock face behind them. Their walls and roof structures acted as heat batteries. The science behind what they built was ignored for most of the modern construction era. It is no longer ignorable. The insulation industry sold you one idea, resistance, and quietly buried the idea that actually wins. Resistance tries to block heat. Mass absorbs it, stores it, and releases it on a delay. A delay you can engineer to work in your favor. The scientific principle is called thermal mass, and it is measured not in R value but in volumetric heat capacity, the amount of heat energy a material can hold per unit of volume. A dense earth and clay composite has a volumetric heat capacity roughly 4 times that of fiberglass insulation by volume. That means it can absorb 4 times as much incoming heat energy before it begins to pass that heat through to the living space below. The key phrase in that sentence is before it passes through, because all materials eventually transmit heat. What you are engineering is the timing. The technical term for that timing is thermal lag. Thermal lag is the delay, measured in hours, between when heat energy enters a material on one side and when it emerges on the other. A 12-inch thick dense adobe or rammed earth layer can produce a thermal lag of 8 to 12 hours. That means heat striking your roof at 2 in the afternoon does not emerge inside your home until 2 in the morning, when outdoor temperatures have already dropped and your ventilation can handle it passively. Think of it this way. A cast iron skillet and a paper plate are both on the same stovetop burner for 60 seconds. The paper plate transmits heat almost instantly. You cannot hold it. The cast iron skillet has absorbed that same energy and is holding it, distributing it, releasing it slowly long after the burner is off. Your fiberglass insulation is the paper plate. A thermal mass roof assembly is the cast iron skillet. One resists briefly, then transmits. The other absorbs, stores, and releases on its own schedule. The Anasazi paired thermal mass with a second principle that doubled its effectiveness: diurnal cycling. Diurnal cycling refers to the natural 24-hour oscillation of outdoor temperature, hot by day, cold by night. A properly designed thermal mass roof assembly doesn't just delay heat entry, it uses the nighttime cooling phase to discharge the heat it absorbed during the day, resetting itself so it is ready to absorb again the following morning. This is the mechanism the cliff dwellings exploited. The sandstone behind them acted as their primary mass layer. The overhanging cliff above them provided strategic shading during the high summer sun angle. The open face of the dwelling allowed cold night air to flush residual heat from the thermal layer before dawn. It was a passive, self-resetting system. The U.S. Department of Energy's Building Technologies Office has since documented that well-designed thermal mass roof systems in hot, arid, and mixed climates can reduce peak cooling loads by 25 to 30% compared to standard insulated assemblies, without any mechanical cooling input. That figure is not theoretical. It comes from monitored test structures. The Anasazi were not guessing. They were engineering. And they had 400 years of iteration to prove it worked. The materials you need are four: a dense earthen substrate layer, a stabilizing binder, a ventilated air gap, and a reflective outer cap. The earthen substrate is a mixture of site clay, sand, and chopped natural fiber. Straw, dried grass, or hemp herds all work. The clay binds. The sand controls shrinkage and cracking. The fiber adds tensile strength to resist thermal expansion stresses. The binder can be natural hydraulic lime, a material that has been used in construction since Roman times and that sets via a chemical reaction with water and carbon dioxide rather than heat, making it suitable for application without any powered equipment. The air gap is a simple ventilated cavity between the mass layer and the outer surface. The reflective cap is corrugated galvanized steel or a lime wash finish over the outer surface, and both of which reflect a portion of incoming solar radiation before it even reaches the mass layer. For the first three steps, begin by assessing your roof substrate. You need a surface that can bear additional dead load. The mass layer will add approximately 10 to 15 pounds per square foot depending on depth, so confirm your roof structure can handle it, or apply the system to a purpose-built shade structure or outbuilding first if you are uncertain. Step 1 is cleaning and dampening the existing roof surface so the first earthen layer bonds correctly. Step 2 is mixing your thermal mass compound, a ratio of 3 parts sharp sand to 2 parts screened clay to 1 part chopped straw by volume, mixed to a stiff but workable consistency with water, never soupy, closer to thick biscuit dough. Step 3 is applying the first layer at a depth of 3 inches, pressed firmly and worked level with a float. Keep a bucket of clean water nearby to dampen your tools and prevent the mix from adhering to them rather than the substrate. Allow this layer to cure for a minimum of 48 hours before continuing. Do not rush this phase. A layer that cracks through drying too fast loses a significant portion of its thermal mass value. Step 4 is the second mass layer, applied at another 3 inches, bringing your total earthen depth to 6 inches. This is your minimum viable thermal lag target, producing approximately 8 hours of delay in summer peak conditions. Step 5 is the ventilated air gap, using 1-inch timber battens nailed or screwed across the cured mass surface at 16-inch centers. You create a cavity that allows air to move beneath the outer cap, carrying away heat before it can conduct downward into the mass. This is the same principle used in ventilated facade systems across Scandinavian construction. The air gap is not cosmetic, it is mechanically functional. And skipping it cuts the system's performance by roughly a third. Step 6 is the reflective cap, a single layer of corrugated galvanized steel laid across the battens and secured with roofing screws gives you a surface that reflects 60 to 70% of incoming solar radiation, dramatically reducing the initial heat load the mass layer has to absorb. If you prefer a non-metal finish, 2 coats of lime wash over a breathable membrane achieve similar reflectivity and allow the mass layer to breathe and self-regulate moisture. Testing conducted by the Earthship Biotexture Project in Taos, New Mexico, an off-grid building system that incorporates thermal mass roof and wall assemblies, recorded interior temperature variation of less than 15 degrees Fahrenheit over a 24-hour period during summer ambient swings of 55 degrees Fahrenheit. Conventional insulated structures in the same region showed interior swings of 30 to 35 degrees Fahrenheit under the same conditions. That is more than double the temperature instability in a house most people would consider well insulated by code. A 6-inch thermal mass roof assembly, properly constructed, holds interior temperatures stable without any mechanical input, without any electricity, without any grid connection. The mass is the machine. On cost, standard blown-in fiberglass insulation to achieve R38 runs approximately $1.20 to $1.80 per square foot installed in most U.S. markets as of recent estimates. A 6-inch thermal mass assembly using site clay, purchased sand, straw, and galvanized steel cap materials runs approximately 60 cents to 90 cents per square foot in materials alone, roughly half the price. Before accounting for the fact that fiberglass requires professional FEAR installation to achieve rated performance while the earthen system can be owner-built. The thermal mass system does not degrade, it does not compress, it does not absorb moisture and lose rating. Its effective performance in year 20 is the same as in year 1. The fiberglass bat you paid full price for is already underperforming before the contractor's truck left your driveway. In 2021, a homesteader named Tomasz, building a 900 square foot off-grid home in rural New Mexico, applied a full thermal mass roof assembly based on Anasazi construction geometry. South-facing, 6-inch earthen substrate, ventilated batten gap, galvanized cap. He recorded interior summer high temperatures averaging 74 degrees Fahrenheit with no mechanical cooling, against outdoor highs consistently above 98 degrees Fahrenheit. His total roof material cost was $380. The International Building Code's 2021 edition acknowledges thermal mass as an alternative compliance pathway to standard R-value requirements under Section C 402.2.1, meaning this is not fringe science. It is a recognized, code-acknowledged thermal strategy that most contractors simply don't know how to build. The power grid does not have to fail completely to destroy your thermal safety margin. It only has to flicker at the wrong time of year. A 3-day heat wave with rolling blackouts turns a code-compliant insulated house into an oven within hours. A thermal mass structure stays regulated for days without any input at all. You can keep wrapping your house in materials designed for laboratory conditions and priced for contractor margins. Or you can build a roof that uses physics, the same physics the Anasazi used for 4 centuries in one of the harshest climates on the continent. One of those choices depends on the grid. The other one doesn't. Your move.